Welcome to This Explainer. Today, we're diving straight into the hidden realities of amputation. And honestly, we're going to explore some absolutely awe-inspiring, high-tech medical innovations that are bridging the gap between human resilience and bionic solutions. I'm literally thrilled to guide you through this today. We're looking closely at that wild intersection of human biology and cutting-edge engineering, unpacking how modern medicine is quite literally rewiring the human body.
Here's our roadmap for today. We'll start with the complex neurology of chronic pain in Section 1, then move right into clever rehab techniques in Section 2. After that, we'll tackle the mechanical hurdles of prosthetic sockets in Section 3, and wrap up with a mind-bending look at modern surgical tech and our bionic future in Sections 4 and 5. Let's get into it.
All right, Section 1, the hidden pain of amputation. We need to acknowledge a pretty harsh truth right off the bat. For 30 to 80% of patients, the physical loss of a limb, well, it's really just the beginning of a chronic, invisible battle. Actually, medical literature going all the way back to the Civil War, specifically the writings of neurologist Silas Weir Mitchell, documented this exact phenomenon. But for the longest time, it was stigmatized. People thought it was purely psychological. Today, though, we know for sure it's a very real, intense, physiological battle.
So it presents the ultimate paradox. How on earth can a missing limb still hurt? I mean, it's gone, right? Well, the answer lies in the incredible and honestly, sometimes super frustrating adaptability of our nervous system. When a limb is removed, those severed nerves can just spontaneously fire. Doctors call these ectopic discharges, which is really just a fancy way of saying random electrical misfires. But the issue goes way deeper than that, right into the spinal cord and the brain itself.
Now, it's absolutely crucial to draw a clear line here between localized physical nerve injury, which we call RLP, or residual limb pain, and the brain's complex sensory mapping errors known as PLP, or phantom limb pain. RLP happens right at the surgical site. It's often caused by poor healing, an infection, or this tangled knot of injured nerves called a neuroma. But PLP? That happens in the absent limb. It happens because the brain's somatosensory cortex, the area that processes touch and feeling, actually reorganizes itself. So the brain areas that used to get signals from, say, a missing hand, suddenly start getting input from other nearby body parts. It's kind of like a totally confused biological GPS system, creating this highly painful mapping error.
Doctors attack these dual threats with a huge array of pharmacological tools. We're talking everything from everyday anti-inflammatories like paracetamol for general post-op pain to heavy-hitting NMDA antagonists like ketamine for acute phantom pain. You'll also see anticonvulsants like gabapentin used to basically block those faulty nerve signals. But here's the catch. Finding a lasting cure strictly through medication, it's incredibly difficult. And relying on opioids long-term carries risks we all know about. So we really need more than just chemistry to solve this.
Which brings us to Section 2. Tricking the brain. Because if the brain is making a mapping error, well, maybe we can trick it into fixing itself. This is where rehab gets incredibly creative.
A brilliant, almost unbelievably simple example of this is mirror therapy. It is astonishingly low tech. By simply placing a mirror to reflect the intact limb, the patient watches the reflection move. And get this, their brain is tricked into believing the missing limb is still there and perfectly healthy. It completely outsmarts our own complex neurology. This simple visual feedback actually helps reverse those maladaptive cortical changes we just talked about.
And now, modern technology is scaling up that exact same concept. By using fully immersive virtual reality, we can convince the brain the limb is still there, which drastically drops pain levels. I mean, studies show an awe-inspiring 50 to 90% reduction in phantom limb pain using VR training. There's no way around it. That is a real game changer. The brain is led to believe the missing limb is intact and controllable, giving patients profound relief without a single pill.
But okay, even if we manage the neurological pain perfectly, we still have to confront a massive mechanical hurdle. Section 3, the prosthetic socket problem. Since the modern era of prosthetics kicked off after World War I, attaching an artificial limb has mostly meant strapping the residual limb into a rigid socket.
And the daily reality of that? Well, up to half of all prosthetic users struggle with severe socket problems. They're battling daily volume fluctuations, which means their limb is literally changing size throughout the day. Add to that painful skin conditions, sweating, inadequate suspension, and just the general awful discomfort of sitting down while strapped into a rigid cup. For some patients, these mechanical issues are so bad, they just abandon their prosthesis entirely.
To solve this, innovators have come up with brilliant new casting systems, like the Symphony water casting device you see here.
Instead of using messy, traditional plaster that might not even capture the limb perfectly, this system uses a cylinder filled with water blotters. It applies constant, perfectly even fluid pressure right across the patient's limb while they're bearing weight, so it captures the exact shape under actual load. This creates a vastly superior socket fit in just a matter of minutes. It's a massive upgrade for daily comfort.
But what if we could just bypass the painful, cumbersome prosthetic socket altogether? That brings us to Section 4, fusing bone and machine. This right here is the bleeding edge of medical science.
The absolutely crucial concept here is osseointegration. It's an awe-inspiring surgical procedure where medical engineers literally fuse titanium directly into the human skeleton. It was initially pioneered back in the 1950s by Per Ingvar Brennemark, and the technique allows a patient to just snap their prosthesis onto a percutaneous fixture, basically a metal post safely extending out through the skin. It completely eliminates the need for a traditional socket, the whole shebang.
Looking at systems like the Opera implant, you can see how a threaded titanium fixture integrates directly inside the canal of the femur bone. Then, after a healing period that lets the bone actually grow right into the metal, an abutment is attached that protrudes safely through the skin. The bionic leg then attaches directly to this abutment. And the benefits? Huge. It improves hip range of motion, sitting comfort, and it even provides a kind of sensory feedback called osseoperception, as vibrations travel from the ground straight up into the skeleton.
Now, as sci-fi as this incredible technology seems, it is heavily grounded in medical reality. And that means strict health criteria to prevent devastating infections or bone fractures. Patients cannot have diabetes, peripheral vascular disease, or osteoporosis. They also can't be active smokers. Because this surgery involves a permanent opening in the skin, the body's healing and immune systems must be in absolute top shape to maintain that implant safely over time. Section 5. The Bionic Future. Okay, so we've securely attached the machine directly to the human bone. Incredible. But how do we achieve seamless, lifelike control over that robotic limb?
Well, when surveyed, the ultimate desire for amputees isn't just physical restoration. It's the return of intuitive, thought-driven control and genuine sensory feedback. Patients don't want to awkwardly flex a shoulder muscle just to make their bionic hand close, right? They want to simply think about closing their hand and have it happen instantly, just like you or I, Hugh.
And this is made possible through something called targeted muscle reinnervation, or TMR. This surgery acts exactly like rewiring a house. Medical professionals take the severed nerves that used to control the missing hand, and they literally plug them into new, intact muscle targets, like the bicep or chest muscles, which honestly aren't biomechanically functional in the exact same way after an amputation anyway.
The sequence of events here is incredibly elegant in practice. Thanks to this internal rewiring, a patient only has to think about moving their missing hand. That thought travels down the old nerve, but instead of hitting a dead end, it fires into the new muscle target. That muscle contracts, generating a clear electrical signal on the skin. Then, surface electrodes read that exact signal and instantly close the bionic hand. It restores simultaneous, highly intuitive control. It's brilliant.
But what's truly astonishing, and honestly perhaps the greatest victory in this entire explainer, is the secondary medical benefit. Giving these severed nerves a new muscle to talk to actually prevents them from forming those painful neuromas. It reverses the maladaptive brain changes we discussed at the very beginning, acting as a massive cure for chronic post-amputation pain. We are literally solving the software error by giving the biological hardware a new outlet. How cool is that? As we perfect this incredible fusion of biology and technology, what you should really take away from this explainer is a question. How soon will fully integrated neural interfaces, combining bone anchors, muscle rewiring, and virtual reality, make the line between human and machine disappear entirely? The future of human resilience isn't just healing, it's upgrading. Thank you so much for diving into this fascinating subject with me. Keep wondering, keep learning, and I'll see you in the next explainer.